Hi, Chem 101 students, and welcome back for another lecture on acid-base chemistry. And this one's going to be focused on pH and how to calculate pH and what it is and how to calculate it. So we've discussed in the previous lecture the hydrolysis of acids and bases, and we also talked about how water is amphoteric. It can behave as both an acid or a base. And in fact, to some extent, water behaves as an acid and a base with itself. And it's a very small extent, but there will always be a few water molecules where the one water molecule will give an H plus to the other. And so in this case here, the acid would be this water molecule, and the base would be this water molecule. And this is the right water molecule is the acid here, the way I've drawn it anyway, because it's giving the H+. That's what acids do. And the left water molecule is the base because it's accepting an H+ or accepting a proton. And so the result is that the left water molecule here now has 3 H's, and also the charge has gone up by 1 from 0 up to +1. It has gained a proton. And the H2O has lost a proton, so now it doesn't have 2 H's, it only has 1, and also the charge goes down by 1 from 0 down to -1. And I've drawn a double arrow here because this is an equilibrium. In fact, very few water molecules actually do this in pure water, but a few of them do. So you get a little bit of these hydronium and hydroxide ions even in pure water. And these are mediated by this equilibrium here. So whenever you have acids and bases in water, remember acids make hydronium in water, bases make hydroxide. So whenever you have acids and bases in water, they're going to be subject to this equilibrium, the balance of hydronium and hydroxide here. And in pure water, the concentrations of hydronium and hydroxide multiply to 1 × 10⁻14. Which is also known as K molar, or Kw rather, the equilibrium constant for water, as it's called. These concentrations would be in molarities. So let's discuss the implications of that for water. So water is neutral when you have equal concentrations of hydroxide and hydronium. Going back, looking at this, if this reaction is making hydroxide and hydronium in pure water, every time one hydronium is made, one hydroxide is also made. So that means the concentrations of both must be the same if you're in pure water. And so if they are the same, that means they are both 1 × 10⁻⁷. Why is that? Well, it's because Kw, 1 × 10⁻14, is the concentration of hydroxide times hydronium. So if we take the concentration of hydroxide times the concentration of hydronium, these are supposed to equal to 1 × 10⁻14 if we have pure in water here. They're supposed to always multiply to 1 × 10⁻14 if the concentrations are in molar. And indeed, if the concentration of hydroxide is 1 × 10⁻⁷, and the hydronium is the same at 1 × 10⁻⁷, that multiplies to 1 × 10⁻14. And the way we can do that is if you multiply two numbers that are the same, like 10 here, and with exponents, you can get the result by adding the exponents. So -7 plus -7 is -14. If you don't remember that, that's okay. You can just use your calculator here. 1 × 10⁻⁷ times 1 × 10⁻⁷ equals 1 × 10⁻14. And so that works too. So in pure water, these concentrations are equal. They would both be 1 × 10⁻⁷, and it's important to note that the unit here that we're talking about is molarities, moles per liter, or the concentration. So in pure water, they're both the same. They're both 1 × 10⁻⁷. Now, if if they're not pure water, let's say you add acid to this pure water. Well, now you're increasing the concentration of hydronium, but the concentration of hydronium and hydroxide still have to multiply to kW, 1 times 10 to the minus 14. So let's say we dump in enough acid to increase the concentration of hydronium to 1 times 10 to the minus 4 instead of 1 times 10 to the minus 7. That means the concentration of hydroxide must be 1 times 10 to the minus 10, because concentration of hydroxide times the concentration of hydronium has to be equal to, in water, 1 times 10 to the minus 14 if we're at room temperature. So if the concentration of hydronium is 1 times 10 to the minus 4, well, not 14, but 4, 1 times 10 to the minus 4, still these two concentrations have to multiply 1 times 10 to the minus 14. So that means the concentration of hydroxide must be 1 times 10 to the minus 10, because negative 10 plus negative 4 is negative 14. Or if you were to use your calculator, 1 times 10 to the minus 10 times 1 times 10 to the minus 4 equals 1 times 10 to the minus 14. So what this means is that if the concentration of hydronium is increased because you have added acid to the pure water, let's say, then the concentration of hydroxide must be less. It must be decreased, because they always have to multiply to 1 times 10 to the minus 14. So as one gets bigger, the other one must get smaller to maintain that equilibrium. On the other hand, if we have a basic solution where we have added, let's say we add sodium hydroxide to the water, which increases the concentration of hydroxide, that means the concentration of hydronium must be lesser, because if, for example, we add enough sodium hydroxide to increase the hydroxide concentration to 1 times 10 to the minus 4 molar, then the concentration of hydronium must be 1 times 10 to the minus 10 molar, because these will now multiply to 1 times 10 to the minus 14, and that equilibrium is maintained. And so due to this autoionization of water and this equilibrium that is maintained in water, the concentration of hydroxide and hydronium in water must always multiply to 1 times 10 to the minus 14 in room temperature water. So notice when we're talking about how much hydronium or hydroxide concentration in the solution, we're always saying like 1 times 10 to the minus 7 molar hydronium or something like this. It's a lot of words to say. And so people don't like to have to do that when they want to talk about how acidic or neutral something is. So often when they're trying to talk about the concentration of hydronium, what people will instead use is the pH, and the pH is defined as the negative logarithm of the hydronium concentration, or the negative logarithm of the proton concentration. Remember from the last lecture, aqueous protons and hydroniums are really two ways of saying the same thing. They are interchangeable. And so I'll use either one. I often like to write H+1 because it's shorter, but that an aqueous H+1 ion is the same thing as a hydronium ion. So let's talk about what this means for pH now. What we're going to see is that when pH is 7, that means a neutral solution. When pH is greater than 7, that indicates a solution that is basic, meaning it has more hydroxide than hydronium. When pH is less than 7, we say it's acidic, meaning it has more hydronium and less hydroxide. So let's first talk about calculating the pH when we have a integer pH value, which would happen when hydronium concentration is 1 times 10 to the minus some whole number up here. So for example, let's say the concentration of hydronium is 1 times 10 to the minus 7 molar. Well, then the pH equals the negative log of this concentration. So it's going to be the negative log of 1 times 10 to the minus 7 molar. So depending on your experience with algebra, you guys have probably taken college algebra, it's a prerequisite for this class, but you may not be that comfortable with logarithms. Just a simple definition of what logarithm means. A base 10 logarithm, which is indicated by log here, is basically the opposite of 10 to the power of something. If you have 10 to the power of something, log undoes 10 to the power. That's what it means. And so if we're looking at this here, given that log undoes 10 to the power, we can see we have 1 times 10 to the minus 7. Well, we can forget about the 1. Anything times 1 is itself. So we have log of 10 to the minus 7. Well, log undoes 10 to the power. So log cancels 10 to the power there. And so then also, then that gives us just negative 7. But a negative times a negative is a positive. So the negative cancels the negative and we get 7. So therefore, when the concentration of hydronium or protons is 1 times 10 to the minus 7, the pH is 7. And that is what happens when you have neutral water. Neutral water has the same concentration of hydronium and hydroxide. They're 1 times 10 to the minus 7. So if you have neutral water or neutral solution of any kind, the pH will be 7. Now, if you have a hard time remembering that log undoes 10 to the power, even though you don't need a calculator to do this, you saw how I was able to do it without the calculator. If we have 1 times 10 to the power, we can put it in the calculator. And the way you would do that is you'd put negative and then you'd put log. And so you have a log button here in your calculator. And I'll go into more detail on this later. Then you do 1 times 10 to the minus 7. If you put that in your calculator, it will give you the pH, which is 7. But if you have, a 1 times 10 to the power, you don't really need the calculator because you can, as long as you understand that log undoes 10 to the power, then you can get the pH that way. Now, let's say the proton or the hydronium concentration is higher than it would be in neutral solution. It's 1 times 10 to the minus 4 instead of 1 times 10 to the minus 7. Then likewise, the pH equals the negative log of 1 times 10 to the minus 4, which is just the same way as saying 10 to the minus 4. Okay, that's why I crossed out the 1 up there. So again, just remembering what log means, log undoes 10 to the power. So log gets rid of 10 to the power, and so we just have the negative of negative 4, and then negative cancels to the negative, and we have 4. So if the concentration of hydronium is higher than hydroxide, it's 1 times 10 to the minus 4, then the pH will be 4. The pH is less than 7, that indicates an acidic solution. If the concentration of hydronium is less than it would be in pure water in a neutral solution, let's say it's 1 times 10 to the minus 9 molar, then just the same way we did it here, the pH would be 9. So when the pH is greater than 7, that is indicating a basic solution. So if you have, a hydronium concentration that's 1 times 10 to the minus something, it's relatively straightforward to get the pH even without a calculator. But what if you have a non-integer pH value? So what if you don't have 1 times 10 to the power? You have like 2.3 times 10 to the power. Well, then you're going to have to use your calculator to do the log. You won't be able to just do it the easy way like we just did. So first of all, you're going to want to know if you have a double line calculator like my Casio here. Clear. I just want to clear this out. Clear. Okay. Or if you have a single line calculator like this Windows calculator here. Now, if you have a double line calculator, when you press log, the calculator will just display log on the screen like you see here. But if you have a single line calculator and you press log, it will give you an error. And this is because you need to put the number in first and then take the log of it. So I'm going to give you 2 sets of directions that will work with either a double line calculator or a single line calculator. if you have a double line calculator like the Casio and you press log and it says log on the screen, use the directions in yellow on these slides. If you have a single line calculator like the Windows calculator and it gives you an error when you press log on an empty screen, then use the blue instructions that I'm about to give you. Okay, so let's start. What is the pH when the hydronium concentration is 2.5 times 10 to the minus 3 molar? So remember, pH, the definition, is the negative log of the hydronium or the proton concentration. So we're going to have to take the negative log of this value here. Now, if we have a double line calculator, again, if you have a double line, calculator like the Casio, you're going to use the yellow instructions. So you're going to press the negative sign, which will either look like parentheses negative like this or plus / minus. Then you'll press the log key like this. Then we make sure to use our EE or EXP too. We put 2.5. Then we use our EE or EXP. On the Casio, it looks like times 10 to the power. So like that, just whatever you do, don't type out times 10 to the power. Use your EE or EXP or this key right here. And then we'll push the negative sign again, and then we'll push 3. And then we get pH of 2.6. Of course, there's lots of extra digits, but don't write all of those. Write 2.6 or 2.60 would be okay too. Okay, now if we have a single line calculator, the way we're going to do this is we're going to have to put in the number first and then hit the log. So we're going to press 2.5 first, then we're going to hit our EE or our EXP, and we're going to put the negative 3, and then hit the negative sign. There we go. And then we'll press the log key. So now we press log and it takes the log. Then we have to change the sign because it's the negative log. So we hit the plus minus again and that changes the sign. And we get pH 2.6 or 2.60 if you like. So depending on your calculator, again, if you have a dual line calculator, use the yellow instructions to take your logs and get the pH. If you have a single line calculator, use the blue instructions. Let's do one more. What is the pH when hydronium concentration is 6.8 times 10 to the minus 12? Again, on the dual line calculator, we press first negative and then log. And then we're going to put this in, making sure to use our EE or EXP. We press 6.8 first. Then we do EE or EXP, or in this case, my button's right here. And then I do negative, and then I put 12 equals. And I get a pH of 11.2 about, or 11.17. Now, if you have a single line calculator like the Windows calculator here, instead you're going to put this number in first. You're going to push 6.8, press EE, then 12, and then make it negative. Like that. So now we have our 6.8 times 10 to the minus 12. We're going to log that, and then remember the pH is the negative log. So then we change the sign and we get the same pH here. So our pH was 11.17. Don't write too many digits. I'll give you a pass on sig figs here for logs because the rules for sig figs on logs are different than they are for adding and subtracting, multiplying and dividing, and I'm not going to teach those to you, but don't be writing every single digit on the calculator. Your calculator doesn't understand sig figs, remember? Okay. Now, what about when we have hydroxide concentration? Now that's a little bit more difficult because the pH is the negative log of the hydronium concentration, not the hydroxide concentration, but we do have a way to get the hydronium concentration if we have the hydroxide concentration. We have to remember that we have Kw, which is 1.0 times 10 to the minus 14, and that equals the concentration of hydronium times the concentration of hydroxide. So if we have the hydroxide concentration, we can get the hydronium concentration, all we have to do is take both sides here and divide by the hydroxide concentration. That will cancel the hydroxide concentration on this side, and on the right side we'll just have the hydronium concentration. We also have to do it on this side. So first we're going to need to get the hydronium concentration by taking 1 times 10 to the minus 14 and dividing by the hydroxide concentration. Then we can take the negative log of that to get the pH. So yes, first determine the H+1 or the hydronium concentration. Remember that proton times hydroxide concentration is 1 times 10 to the minus 14. So as we saw here, the hydronium or the proton concentration, remember either one means the same thing, will be 1 times 10 to the minus 14 over hydroxide concentration. So we're going to plug that in. Our hydroxide concentration is right here, 7.3 times 10 to the minus 6. We're going to put that in right there. And now we have to put this in our calculator. Make sure that you are using your EE or EXP button. So we do 1 times 10 to the minus 14, and we're using our EE. You're never typing times 10 to the power, remember? Use your EE or EXP. And we'll do divide by 7.3 EE negative 6. And so we get that the hydronium concentration is about 1.4 times 10 to the minus 9. And so we're going to write this right down here, 1.4 times 10 to the minus 9. Now we can get the pH. The pH is going to be the negative log of this proton or hydronium concentration. So it's a negative log of 1.4 times 10 to the minus 9. Here's where you put it in your calculator. And so I'm just going to use the dual line one here. So it's going to be the negative log of 1.4 EE negative 9. And we get a pH of about 8.9. And that's how you figure out the pH if you're given the hydroxide concentration. Okay, so there's one extra step if you're trying to get the pH when you have the hydroxide concentration. You first have to convert to hydronium concentration or proton concentration. Then you can take the negative log of that to get the pH. Remember, pH always comes from the hydronium. Now, when it comes to pH calculations, there's a lot of places you can start and there's a lot of places you can get at. So let's first go to a couple more definitions here. So you already know the definition, pH equals negative log of hydronium. So if you have hydronium concentration and you want to get pH, you take the negative log of that. But what if you have the pH and you want to get the hydronium concentration? Well, remember how I told you that log is the opposite of 10 to the power? Well, 10 to the power is also the opposite of log. And so the way that I get to this equation is like this. If I have pH equals negative log of hydronium or H plus concentration, I can take 10 to the power of both sides. Oh, first I can multiply both sides by -1. So I'm going to multiply times -1 times -1. And so that's going to give me now the negative pH. And this is going to cancel my negative here. That equals the log of the hydronium. And as I said, log is the opposite of 10 to the power. And also, 10 to the power is the opposite of log. We call that the anti-log. So if I take 10 to the power of both sides, I get 10 to the power of negative pH here. And then I get 10 to the power of log hydronium. 10 to the power cancels out log. And so ultimately we get that 10 to the negative pH equals the concentration of hydronium. Now, do you need to know how to do this algebra that I just did? No. You should have this equation handy though. Hydronium concentration is 10 to the power of negative pH, or this is also said as the anti-log of the negative pH. 10 to the power is also called the anti-log. Now, besides pH, there's also an analogous definition for hydroxide. It's called the pOH. So the pH is a negative log of the H plus concentration. The pOH is the negative log of the OH minus concentration. And likewise, if you want the hydroxide OH minus concentration, it's 10 to the minus pOH. So these two equations are the hydroxide analogies for hydronium here. Finally, we had this equation I showed you earlier. We've been using this all along the way in this lecture. Hydronium concentration times hydroxide concentration always multiplies to 1 times 10 to the minus 14. A kind of easier version of this equation that I like to use a lot is pH plus pOH equals 14. So these two are basically the same equation. It's just this one is said in terms of hydronium and hydroxide concentrations, and this one is said in terms of pHs and pOHs. So this one obviously is a bit easier to use, so I often like to use that, and I will show you how you could use it if you want to too. Now, if you want to, here's a diagram here showing you how you can get between all of these measurements, hydronium concentration, hydroxide concentration, pH or pOH. So if you are just going from one space to another here, one step, I have all of the equations for the one step here. If you want to go between pH and pOH, you use the fact that pH and pOH add to 14. So for example, if you want pOH, let's say we want pOH right here, well, we could subtract pH from both sides, so that will cancel a pH here. If we subtract pH here, we get now that pOH equals 14 minus pH. And so if we have pH and we want to get pOH, we have pH equals 14 minus pOH. Now, if you have these in your notes, you can just look and say, okay, I want to go from pH to pOH. Oh, well, I'm going to go along this arrow here, pOH equals 14 minus pH. Or if I have pOH and I want to get pH, oh, pH equals 14 minus pOH. That's from the same equation, just manipulating it to solve for pH instead of pOH. Likewise, if you want to go between pH and hydronium concentration, well, if you have hydronium concentration, you want to get to pH, the pH is the negative log of the hydronium or the H plus concentration here. That's this equation here. If you have pH and you want to get to hydronium, you're following this arrow here. The H plus concentration, the hydronium concentration, is 10 to the minus pH. That's these equations right here. If you want to get between pOH and hydroxide, you use these equations here in much the same way. Finally, if you want to get between hydronium concentration and hydroxide concentration, you will use this equation here, just like we did in the last example. If you have hydronium concentration, you want hydroxide concentration, well, the hydroxide concentration is 1 times 10 to the minus 4 divided by the proton, or the hydronium concentration. Likewise, if you have hydroxide and you want to get hydronium, the hydronium concentration is 1 times 10 to the minus 14 divided by hydroxide. So this little diagram here summarizes everything you might want to do with these equations. And then if you're one step away in this diagram, solving your problem will only require one step. But if you're 2 steps away, if you want to go from pH to hydroxide, that's going to take 2 steps. You'll have to go to pOH first and then hydroxide, or you could go from pH to hydronium and then to hydroxide. Either of those directions will work. If you're starting at hydronium and you want to get at pOH, you could either determine pH and then, get to pOH, or you could determine hydroxide and use that to get pOH. So this is a nice little handy dandy summary for you to have for your pH calculations in your notes next to you. It includes all the equations that we have talked about so far. So given any one of these four quantities, you can determine the other three. You just follow the steps here in this diagram. So let's use this to do a few questions. So in the questions that I'm going to give you about pH and pOH, I will give you one of these four values, either the hydronium concentration, the hydroxide concentration, the pH, or the pOH. And I will ask you to determine the other three. So each of these lines is a different problem. There are four problems here. In this problem, I've given you the hydronium, and I want you to get the rest of the variables here. In this one, I've given you the hydroxide. I want you to get hydronium and pH and pOH. Here, I've given you pH, and I want you to get hydronium hydroxide and pOH. Here, I've given you pOH, and I want you to get all the rest of these three here. Also, based on the pH, you should be able to tell me if the solution is acidic or basic or neutral. Based on what the pH is. If pH is 7, it's neutral. If it's less than 7, it's acidic. If it's greater than 7, it's basic. So let's start by doing these ones here first. So I'm gonna start by taking hydronium and convert to hydroxide. I'm also going to take hydroxide and convert to hydronium. So to fill out this part of the table, I'm going to need these two right here. I'm going between hydroxide and hydronium. I'm using this part of the diagram. So I'm going to do 1 times 10 to the minus 14 divided by the concentration of the one that I don't have. So in this first problem here, I'm given hydronium concentration as 8.3 times 10 to the minus 9 molar. And if I want to go between hydronium and hydroxide concentration, I take 1 times 10 to the minus 14 and divide that by the molarity that I'm given. And so in this case, again, we're using this formula. 1 times 10 to the minus 14 is hydronium times hydroxide. So what we have here is we have hydronium, we want hydroxide. And so we would solve this top part for hydroxide. We would do this by dividing both sides by hydronium. So if we divide this side by hydronium concentration, that will cancel the hydronium concentration and give us just hydroxide concentration. We would also need to divide by hydronium concentration over here as well. And so that's where we get this here. So our hydroxide concentration will be 1 times 10 to the minus 4 divided by our given hydronium concentration. So hydroxide concentration is 1 times 10 to the minus 14 divided by our given hydronium concentration. So now we're going to plug this in right here. Okay, so we got now 1 times 10 to the minus 14 divided by our hydronium concentration. And now we're going to plug it into our calculator. This time I'll use the single line just to kind of switch it up so you guys, so those of you with single line calculators can see it too. We're going to do 1 EE 14 minus, so 1 times 10 to the minus 14, divide by 8.3 EE 9. Oops, I did that wrong. Divide by 8.3 EE 9 and make that a negative. And we get that the hydroxide concentration is 1.2 times 10 to the minus 6 molar. Don't forget the unit. Molarities is the unit we're working in here. Don't forget the unit on the end. Okay, so we've figured out the first part now. We've taken the hydronium concentration, 8.3 times 10 to the minus 9, and converted that to hydroxide concentration. Now the second line wanted us to take the hydroxide concentration, which was 3.6 times 10 to the minus 5 molar, and turn that into hydronium concentration. We'll use the same approach. It's going to be 1 times 10 to the minus 14 divided by what we were given. So in this case, if we're doing the algebra, of course you already have the solved equations that I've given to you in your notes, so you wouldn't necessarily have to do this algebra, but if we're solving this Kw equation for hydronium, which is what we want, we would divide both sides by hydroxide, which would cancel the hydroxides here, give us just hydronium. We'd also have to divide this by hydroxide concentration. And so we get the hydronium concentration is 1 times 10 to the minus 14 divided by the hydroxide concentration. So now we're going to plug in the hydroxide concentration right here. So we have hydronium is 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 5. And now let's plug that into our calculator. 1 EE minus 14 divided by 3.6 E minus 5 equals. And we get that the hydronium concentration is 2.8 about times 10 to the minus 10 molar. And so now we have figured out these first two parts. We converted the hydronium concentration to hydroxide for this first question. We got 1.2 times 10 to the minus 6, I think. Yeah, right there. And whoops, and then we converted the hydroxide concentration to hydronium concentration, and we got 2.8 times 10 to the minus 10 molar. Now next, we'll want to get the pH and the pOH. So remember, pH is the negative log of the hydronium concentration, pOH is the negative log of the hydroxide concentration, and we've got both of these, so we can figure out the pH and the pOH. So to get the pH, so remember the definition of pH equals the negative log of the hydronium concentration. And we had in part 1 that the hydronium concentration was 8.3 times 10 to the minus 9. So if we are using our double line calculator, let's see. Yeah, we're going to we're going to type it just like we see here for the double line calculator. So it'll be negative and then log, and then we put our number 8.3, don't forget to use the EE, and then negative 9. And we get a pH of about 8.1, 8.1 for the pH. Now, if you've got a single line calculator, so that, yeah, I did this one on the double line calculator. I got pH of 8.1. So our pH is 8.1 on the first line. pOH would be the same thing, except we'd take the negative log of hydroxide. I'll show you that on the subsequent slide. Now, for the second problem, we got that the hydronium concentration was 2.8 times 10 to the minus 10. So the pH will be the negative log of that. So here I have blue instructions, which are the instructions for the single line calculator. For the single line, we put the number inside the log in first. So we press 2.8 first, 2.8 first. Then we hit our EE or our EXP, we put in our 10 and we press the negative. So now we have 2.8 times 10 to the minus 10. We hit the log and then we press the negative sign to change the sign. And so we get a pH of about 9.6 for the second problem. So these are the results we got here. We got, in this one, we got a pH of 8.1. In the next one, we got a pH of 9.6. Now, but what about the pOH? So pOH is done the same way as pH. We just do the hydroxide concentration instead, the negative log of the hydroxide concentration. So I'm just going to show you this on this slide now. I'll do the double line calculator for this one here. So the pOH is the negative log of the hydroxide concentration. So we say negative log, then 1.2 EE minus 6, and we get a pOH of 5.9. And then for the pOH on this line here, it's going to be the negative log of this hydroxide concentration. I'll use the single line calculator here. So we got to put in this value first. We press 3.6 EE 5 and then make that negative. So we have 3.6 times 10 to the minus 5 for the hydroxide concentration. We take the log of that and then we change the sign and we get a pOH of 4.4. Finally, to know if the solution is acidic or basic, we look at the pH. If it's greater than 7, it's basic. If it's less than 7, it's acidic. pH in both of these cases is greater than 7, so these solutions are basic. Now, another thing you might notice is there was another way we could figure out pOH, and that is the fact that we know that pH and pOH add up to 14. So look at this, 8.1 plus 5.9, 8 plus 5 is 13, and 0.1 plus 9 is 1. So 8.1 plus 5.9 is 14. Of course, they add up to 14. Or 9.6 plus 4.4 add up to 14. So that was another way we could have gotten the pOH by solving that pH plus pOH equals 14. I'll use that for our next set of values here. So let's go ahead and answer the last two questions now. Remember, it's true that pH and pOH add up to 14. And also that when the pH is greater than 7, the solution is a base. And so that's what I was just pointing out on the last slide there. Now, if you have the pH and you can find the pOH and vice versa, because pH and pOH add up to 14, that's really handy. So if the pH is 5.3, so remember, pH plus pOH add up to 14. So if we want the pOH, then we're going to solve for pOH by subtracting out the pH from both sides. And so we get this equation that pOH equals 14 minus pH. And so if the pH were 5.3, then pOH equals 14 minus 5.3, and that is 8.7. By the way, also notice that pH is less than 7, so this solution is an acid. Likewise, if we have pOH and we want pH, the pH will be 14 minus the pOH. So pH is 14 minus, in this case, 2.1 for the pOH, and so 14 minus 2.1 is 11.9. That would be a base. And so these are examples of ways that you can interconvert between pH and pOH. And you'll notice that I just did the problems. I just did the problems we had right here. So on the third line, we had the pH, it was 5.3. We figured out the pOH, 8.7. On the fourth line, the pOH was 2.1 given to us, and we figured out the pH 11.9, and so now those values are in here. And we've also been able to determine already if these are acids or bases based on the pH. If the pH is less than 7, it's acidic. If the pH is greater than 7, it's 11.9. All we've got left now is to figure out the concentrations of hydronium and the concentration of hydroxide. And we have the pH and the pOH, so we can use those to get the hydronium and the hydroxide concentration. So we're going to use the antilog. So remember, we've got two equations here. The equations are the hydronium concentration equals the antilog, or 10 to the power of the negative pH, and we have that the hydroxide concentration equals the antilog of the negative pOH. And so we're going to use these equations to figure out the pH and the pOH. Now on line number 3, our pH was 5.3. And so our hydronium concentration is going to be 10 to the minus 5.3, or also known as the antilog of negative 5.3. Now, if you have a double line calculator like my Casio here, you're going to do, you can type 10 to the power, but I don't recommend it. If you look at your log button, above your log button, you should see the antilog, 10 to the power. So the way to get to this is to choose press second or inverse, or in my calculator it's called shift. Press the shift and then the log key, or the second or the inverse and then the log key, and that will get you the antilog. And then you hit negative, and then we're going to put 5.3. The antilog of negative 5.3, that gives us the hydronium concentration. It's 5.0 times 10 to the minus 6 molar. There. Okay. Now, what if you're doing the same thing, but you have a single line calculator? For your single line calculator, you have to put the 5.3 first, then you make it negative, and then usually you have to hit second and then anti-log. On this particular calculator, it has the anti-log right here. So find where the anti-log on your calculator is. If you're having trouble, you can, of course, check your calculator's manual. You could also send me a picture and I will explain to you. Every calculator is a bit different. But here we do the anti-log of negative 5.3 and we get the same thing, a concentration of 5.0 times 10 to the minus 6 molar. And so that's what we just found right here. We found the concentration of hydronium was 5.6 times 10 to the minus 5, 5.0 times 10 to the minus 6 molar. We did that by taking the anti-log of the pH. Now I'm going to figure out the rest of these. So to figure out the hydroxide concentration, so again, let's just write these back. Hydronium concentration is the anti-log of the negative pH, and hydroxide concentration is the anti-log of the negative pOH. So to get the hydroxide concentration, we can take the anti-log of the negative pOH. So I'm going to do that one on the, well, I'll do it on the single line calculator since I have that up. I will hit 8.7, and then I will make it negative because we want the negative pOH, and then I will take the anti-log. And I get about 2 times 10 to the minus 9 molar, which is the answer right here. Now let's do the third line. So to get the hydronium concentration, we want the anti-log of the negative pH. So that one I'm going to do on my Casio. So here I will hit then, I will do anti-log first, so second and log, and then I'll hit negative, and then I'll put in the pH, which is 11.9. And I get a concentration of about 1.3 times 10 to the minus 12, which is right there. And then for the hydronium or hydroxide concentration, I do the anti-log of the negative pOH. So I do shift log again, or second log, or whatever. And then I'll hit the negative, and then I put 2.1. So I'm taking the anti-log of the negative pOH, and that gives me the hydroxide concentration, which is 0.0079 or 7.9 times 10 to the minus 3. Let's see, in standard notation. These are the same number. And so that's how you perform pH calculations. So on your homework, I have a table just like this one where you do a calculation where you get each one of these in 4 different problems, and you have to get the other 3. So that will be good practice for you. If you need more practice, there are problems in the textbook reading as well, which are just the same types of problems that I'm going to give you. But there will definitely be a problem like this on your final exam, so make sure you understand, given one of these 4 quantities, be able to determine the other 3. And so that concludes our discussion about pH. We talked about the definition of pH and pOH, also Kw, introduced a number of equations. Again, if you need a quick reference for this later, this is something you can use. Where did I have it? Right here. This kind of wraps all these equations all up into one handy dandy diagram and tells you which one to use when, but also make sure that you understand which one to use when. In the next lecture, we're going to talk about buffers. And so buffers are solutions that maintain a constant pH. Buffers are extremely important to biological systems. And so that's one of the big reasons why many of you that are going into life sciences are learning about pH right now. And so we'll talk more about buffers and the pH of biological systems like your body in the next lecture. I'll see you then.